Okay, Assalamu alaikum. This is our second lecture, and this is the first lecture that we are basically conducting online. So, this is a recording of the session that I'll upload, and then hopefully you'll listen to it carefully. And I further hope that you will be able to absorb whatever I'm trying to communicate. There is another announcement that I want to make. I posted about that, but let me reiterate that announcement here. Um, uh, in the online session, in the online setup, I guess this is going to last until the 10th of January 2021. So it is going to last for more than 1.5 month or around 1.5 months, something like that. So there won't be any online lab sessions for DLD lab. I do not want to conduct digital logic design labs using simulators. Simulators are also useful, but you should also have a very clear idea about how the actual digital logic devices or hardware or ICs, how do they work, how can you connect those ICs with each other, and how can you interface those ICs with output devices like those 7-segment displays and all that. So I want to conduct the labs inside the actual labs, not virtually online. Therefore, we won't be conducting lab sessions online, but that does not mean that there won't be any activity during those lab sessions. So in the lab sessions, we will have 3-hour lab session. So I'll divide the 3-hour lab session into 2 plus 1. So the 2 hours, I'll try to upload the lecture video before that so that you can watch that lecture video on Monday. I'm talking about the lab session that we typically conduct on Monday. So on Monday, every Thursday, we'll have just the theory session, which will be a recorded session, and you will listen to the lecture recording every Thursday. Then on Monday, we will have the 2-hour recorded video lecture session, and 1 hour would be for Q&A, question and answers. So both sections A and B will conduct 1 hour Q&A session. So the two lectures of each 2 hours session, I hope that before that Q&A session, you would have gone through both those sessions, both those video lectures, and you would have some questions. And if you have those questions, we'll try to address those questions in that live Q&A session. We'll hold that Q&A session either via Google Meet or via Zoom. That is easier. Like we'll decide that, and I'll post about it on Monday. So let's get back to this particular lecture session. Now, this lecture session is a continuation of what we had in our first lecture. In our first lecture, we started to talk about these things. We completed discussion on some things, and then we left some things midway. So we talked about the course learning outcomes. It is very important that you understand these learning outcomes because this is what we are trying to achieve in this course. So by the end of this course, you should be able to check all these learning outcomes. You should have achieved an understanding of the fundamental concepts behind digital logic design. You should have a thorough understanding of the number systems, especially the binary number systems. You should know about these basic gates. This is fairly simple. And the universal gates, the binary coded systems, the especially and most importantly, the arithmetic, the binary arithmetic, the signed and unsigned arithmetic that we do on digital devices, and Boolean algebra, which is basically the foundation on which the whole of this digital universe is created. Then you'll also be expected to have good skills, good design and analysis skills of combinational logic systems. And you should also know about the different minimization techniques that you can use in order to simplify the hardware that is used to implement any Boolean logic function. Then most importantly, you'll also learn about sequential logic systems. Now, we talked about these sequential and combination logic systems. We'll briefly look at them again. So you should also be able to design and analyze those systems as well. Now, we also talked about the grading criteria. Let us not repeat that. And we talked about these digital systems. So I hope you have some understanding of these systems. So this is an example of a typical digital system which has some state information, and that state information is stored in memory. So this is a sequential digital system, and mostly most of the systems that you use, especially related to computing, they are sequential digital systems. They have some sort of memory to store state information. We talked about these different categories of digital system, combination logic systems, where we don't have any memory. The output is directly determined by the inputs. That's it. And then we have sequential logic systems where we have some sort of memory to store state information. We gave examples of these systems. These examples would appear in the coming slides. And we also classified these systems into synchronous sequential systems and asynchronous sequential systems. In synchronous sequential systems, there is a clock signal, and the state of the system is updated at discrete times or at regular intervals or at discrete intervals. It does not happen at any time. Whereas in asynchronous sequential system, the state can be updated anytime. Okay, so it is not like updated on a regular interval. So we gave an example of digital counter. So this is an asynchronous sequential system. Okay. So many of you might use it for the might be using the tasbih counter. So it is an example of a sequential system because it has a state, the count, the number of times you have pressed the count button, and it is asynchronous. Why? Because uh, you do not press that button regularly. It is not synchronized to some clock. You may press it regularly at times, and then you might indulge in some other activity, and you may forget or you may stop pressing the count button. So that is what asynchronous means. It can happen anytime. Then this is the digital computer. We talked about it in detail, and we said that this is a synchronous sequential system. Why? Because every digital computer, it is basically driven by a clock signal. So whenever you buy a computer or CPU or any digital system, so you get this figure, you get this number with it, that this is a 3 gigahertz system or 2.5 gigahertz system. So that gigahertz is basically the frequency of the clock signal that is used to synchronize all activities or all state changes inside that system. So this is a sequential system because it has memory, and this is a synchronous sequential system because everything happens according to that clock. Then we talked about signal, the digital signal, and how that digital signal is represented. Uh, okay, so abstractly, logically, we say we have these digits 0 and 1. They can also be called as false and true, low voltage or high, or just low and high, on and off, or off and on. So we have these different names for these two logical values or these two logical states, these two states. Okay, two binary states. We can name them in any of these ways. Uh, then we said that these two states can be represented differently in different media. So they can be represented. Okay, so this is basically the analog and digital signal. We talked about this, and then we talked about what do we mean by asynchronous. So this is the clock signal or time, and the synchronous signal, it basically changes its state at these specific intervals, whereas the asynchronous, there the change of state can happen at any time. An analog signal, there are no discrete states, and it has continuous values of the magnitude, and it is continuous across time. So, but the digital signal, it has discrete values, like the magnitude is discrete. It cannot have any value. It will have some specific values, and it is discrete along the time axis as well. So it does not occur all the times. The digital value can appear at certain discrete instances of time. that is basically the definition of digital. Here it may be different, but let's see, those things will pan out later on, and you'll have a clear picture of what all these things mean. So we said that the bits can be represented using voltages, and there can be range of voltages that can be used to represent the 1 and 0 bits. Okay. Uh, if we go to another media, the disk, it can be represented by the direction of magnetic field. If we go to optical media, it can be represented by surface bits or light. If we go to dynamic RAM, it can be represented by charge stored on capacitors inside that dynamic RAM. So we talked about these things. And then we talked about number systems again. This is clear. Yeah, like maybe you haven't paid any much attention to this, but this is how numbers are represented. The numbers that you see, decimal numbers or any numbers, basically they represent coefficients of a polynomial, and this is that polynomial. Okay, so the polynomial is in base r. Okay, so r is basically the radix or base in which you're trying to represent any physical quantity, or the magnitude of any physical quantity, or a number, which is basically a number. We talked about this summation. How do we get it? Okay, so this is basically uh, the number that you have. So each digit in the number, it has a specific position. Okay, it has a specific position, and the position is important because the position gives it a certain weight. So this particular digit a naught, it is the least significant digit, and if it were a binary number, then this would have been the least significant bit in the integer part of the number. Least significant means it carries the lowest weight. Okay, so a naught has the lowest weight. So a naught, if it is a decimal number, a naught would be a 1. If it is a binary number, it would be a 1. If it is any base, it would be a 1 because its power is r raised to the power 0. Okay, its weight is r raised to the power 0. This is a1. Its weight is r raised to the power 1. So if it is a decimal number, it is a 10. It represents tens. If it is a binary number, it represents twos. If it is a hexadecimal number, it represents 16s. Okay, and so on and so forth. So when you go to the left, the weight of the number, the digit, it increases or it is multiplied by r. Okay, so this is r raised to the power 0. Its weight is r raised to the power 0. Its weight is r raised to the power 1, r raised to the power 2, 3, 4, 5. Okay, so on and so forth. So if we have an n digit number, so this coefficient is a sub n minus 1, and its weight is r raised to the power n minus 1. Now r can be anything. It can be any base. Uh, so we talked about this. And then the fractional part. So the fractional part here, this is a sub minus 1. So if you just look at the fractional part, this is the most significant digit. Okay, you go to the right, and the powers uh, uh, the powers of these digits, they tend to decrease. So this is, it becomes a smaller and smaller and smaller number, or it becomes, the weight becomes smaller and smaller number. So say for example, if this were a decimal number, then this would be a tenth, 1 by 10. This would be a hundredth, 1 by 100, or 1 by 10 raised to the power 2, or 1 multiplied by 10 raised to the power minus 2. That would be the weight of this number. And if you go towards the right, so the weight would decrease further and further. Okay, so this is the fraction part. So we talked about this. Okay, and how do we, like, how can we reduce a number into these two summations, and how can you find the value of a number using these two summations? Then we talked about, we looked at some general weights in a decimal number system, for example. So we are used to the decimal number system. So we talked about 10 raised to the power 0, 10 raised to the power 1, 2, 3. These are these. Now, since we are like going to transition from decimal to binary, you should remember these values as well. What is 2 raised to the power 0? Any number raised to the power 0 is 1. But 2 raised to the power 1 is 2, then 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8198. So you should remember these powers of 2's. You should remember these powers of 2's. Although you can have access to calculators, but nevertheless, like in many situations, it pays off when you remember these powers of 2 and you can do certain things very quickly. Similarly, you should also remember the negative powers of 2. So 2 raised to the power minus 1 is zero point 0.5, half of zero point 0.5 is then 0.25, half of zero point 0.25 is 0.125, then 0.0625, and 0.03125, so on and so forth. So you should remember at least these numbers. These would be helpful in conversion from one number system to another number system. We talked about this as well. The kilo 2 raised to the power 10. It is not exactly 1000. Kilo is used to refer to 1000, but it's close to 1000. That's why it's called kilo. 1024. Then we have the 2 raised to the power 20. It is a mega. It is basically 1024 times 1024. Then the giga, then the tera, and so on and so forth. These are the common powers of uh, 2 that you should remember, at least up to the powers up 10. Like you should know, you should remember up to 2 raised to the power 10. Okay, the rest are also easy. Like you can easily go to 2 raised to the power 13. But these are useful things to remember. They will help you do things or solve problems quickly. Okay, then we did this as well. How do you convert a binary number to decimal? This is fairly straightforward. Okay, what you need to do is you just need to multiply the digit with its weight or the respective or corresponding power of 2. So look at this number. This is 11010. Okay, so if you start from this particular digit, so this is 0 and its weight is 2 raised to the power 0. So if you multiply this with 2 raised to the power 0, it's going to be 0. So in order to simplify things, like you can only look at the ones and the power of 2's that they need to be multiplied with, and you just need to add those powers of 2's. For example, this is 2 raised to the power, its weight is 2 raised to the power 1, which is 2. Its weight is 2 raised to the power 3, which is 8. So 2 plus 8 is 10. And this is 2 raised to the power 4, which is 16. So 16 plus 10 is 26. So this particular binary or bit combination represents 26 in decimal. Okay, so you can do this conversion. I guess we did it. We did something like this in our last class. How do you convert a decimal to binary? So binary to decimal is easy. This is also easy. It's not that difficult. Again, we did it. Uh, it's not that difficult. Now there are two methods. One, you can use the shortcut. This is the shortcut method basically. If you remember the powers of 2's, you can do it easily. And the other is the proper method. So if you say, for example, we want to convert 625 into binary, okay? So what you can do is you can try to find out the powers of 2's that are present in this number 625, okay? So if you remember the powers of 2's, then it would be easy for you. And if you don't, then it might be difficult, okay? So let me get a pen if I can get one. Let's see. Okay. Let me get not a label, a pen. I need a pen. Okay, so I have a pen. So if you look at 625, 625, like if you remember the powers of 2's, so powers of 2's go from like 0, sorry, 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. Now 625 is smaller than 1025, but it is definitely greater than 512. So the first power of 2 that it has is 512. Okay, so we can write 625 as 512 plus some more powers of 2. Okay, now if you remove 512 from 625, what you get is 113. Okay. Now 113 contains which powers of 2? Okay. So 113, the closest nearest power of 2 is 128, but 128 is bigger than 113. So the next power, the highest power smaller than 113 is 64. Okay. So you can write 113 as 64 uh, plus what? 49. Okay. So if you take 64 out of 113, you get 49. Now 49, the closest powers of 2 to 49 are 64, which is greater than 49, and then 32. So 32 is smaller than 49. 32 is contained within 49. So if you take out 32, what do you have? 32 out of 49, you get 17. Okay, 17 is basically 16 plus 1. The powers of 2 in 17 are 16 plus 1. Okay, so these are all the powers of 2 that are present in 625. Okay, now which powers are these? This is 2 raised to the power 0. I'm just writing the powers of 2 here. Okay, this is 2 raised to the power 0. This is 2 raised to the power 4. This is 2 raised to the power 5. This is 2 raised to the power 6. This is 2 raised to the power 9. Okay. So what would be the binary number that represents 625? So that binary number will have a 1 in the zeros place. Okay. So 2 raised to the power 0, the coefficient of that is 1. There is no 2 here. So the coefficient of 2 raised to the power 1 would be 0. We have a we don't have a 4 in here. We don't have an 8 in here. We have a 16. Okay. Then we have a 32. Then we have a 64. Then we don't have 128. Its coefficient should be 0. We don't have 256. And then we have 512. Okay. So this is 2 raised to the power 0. There is no 2 raised to the power 1, no 2 raised to the power 2, no 2 raised to the power 3. We have 2 raised to the power 4, 2 raised to the power 5, 2 raised to the power 6. We don't have 2 raised to the power 7, 2 raised to the power 8, but we do have 2 raised to the power 9. So this is the binary representation of 625, the decimal 625. This is how you represent it. This is the shortcut. And you can apply the shortcut if you remember the powers of 2. Okay. Okay. So what is the proper method? The proper method is basically repeated division. Okay, subtract the largest. The proper method is basically repeated division of if we want to convert 625 into binary. Uh, for that matter, not just binary. If we want to convert a number from one base to another base, so what we need to do is we need to divide that number repeatedly by the target base. So if we want to convert 625, which is decimal number, to binary base 2, so we should repeatedly divide 625 by 2. Okay, and we should accumulate both the quotient and remainder. We should divide the quotient continuously by 2 unless we get 1 or 0 as quotient, and once we get there we should accumulate all the remainders. Okay, we should accumulate all the remainders in the reverse order of computation. So the first remainder that you got, it would end up here, and the last remainder that you got, it would appear here as the most significant bit. Okay, so we explained this in class. I hope you remember that. And then we talked about these as well, like we are used to commonly occurring bases. We are used to the decimal number system because this comes natural to us. For computing, we need to understand binary. Uh, Octal is useful as well, but more than octal, we need to understand hexadecimal. Okay. Now, hexadecimal is a radix 16 or base 16 number system, and in hexadecimal, okay, I just wanted to change the color, but let us leave that. We have 16 digits. So we can represent 16 different quantities, and in order to represent those 16 different quantities, we need 16 different symbols. 10, we import 10 symbols from the decimal number system, and then for the remaining 6 quantities, we import some symbols from the alphabets, okay, from the English alphabet. So A is not A here. A basically is 10. This is 11. This is C is 12, 13, 14, and 15. So in the hexadecimal number system, A, capital A or small a, it represents the value 10. Okay, and B represents 11, C 12. So these are all useful number systems that we talked about. Then we also talked about, like, in order to be able to, I'm not sure whether we did that or not. In order to be able to do these conversions from binary to octal and binary to hexadecimal, or hexadecimal to binary, or hexadecimal to or octal to binary, you need to remember these combinations. Again, it is not that difficult. So what, like, these are simple. This is simple. These are all just the hexadecimal digits. Okay. This is also simple. It is just these are octal numbers. Okay. Binary is also not that difficult, and decimal is definitely not that difficult. So just uh, I hope you notice one thing. Okay. Now look at this number. This is 10. In decimal, it is 10, and 10 is the base of the decimal number system. Look at this number. This is also 10, and its decimal value is 2. So in binary, in the binary number system, the base, or 2, is represented as 10. Look at this number 10. It is octal. It is 8, and this is the octal number system. In octal number system, the base is represented as 10. Look at this number 10. This is a hexadecimal number, and it represents 16, or the base. So I hope, like, you understand, in any number system, in any base R number system, if you want to represent the base in that number system, it is always 10. Okay, so 10 in decimal is 10. 2 in binary is 10. 2 is the base of the binary number system. If you want to represent the base in the binary number system in itself, so it is 10. 8, which is the base of octal number system, it is represented as 10 in 8. Why? Because you see these digits are going to be multiplied with the powers of 8. So its weight is 8 raised to power 0, and its weight is 8 raised to the power 1. Okay, so this is 0 multiplied by 8 raised to power 0, 1 multiplied by 8 raised to power 1. Similarly, its weight is 16 raised to the power 0, and its weight is 16 raised to the power 1. So the value of this number is 0 multiplied by 16 raised to the power 0 plus 1 multiplied by 16 raised to the power 1, which is 16. So I hope, like, you have noticed this pattern. If you represent any number, uh, for example, if you have a base R system, and in that base R system you want to represent the number R, so it is always going to be 10. Okay, it is always going to be 10. So I hope, like, you can do these conversions. This is 9. This is basically 8 plus 1, 9. This is 8 plus 2, 10. 8 plus 3, 11. 8 plus 4, 12. 8 plus 5, 13. 8 plus 6, 14. 8 plus 7, 15. 2, 0. So 2 eights are 16. Okay, so this is 16 in octal. So this conversion should be fairly simple. If you remember the basic idea of how any number is represented in a particular base, if you remember those equations that we talked about, those summations, if you remember that, then this would be easy for you to understand. Once you understand it, you should try to memorize it. Okay, so this is a good idea that you have memorized these things. Now, the other thing that I guess we didn't talk about it fully, but I guess you know this part of it. Okay. So here we would learn about if we have a number that has both integer part and fractional part. Okay. So how do you convert that number from one base to another? And we'll demonstrate it for decimal to binary and binary to decimal. We'll demonstrate it in those settings. both the integer part and fraction part, and then combining both those things. So we'll demonstrate that, and then you can extend that process to any uh, two base systems. So let's look at an example. First, understand the procedure. The procedure is, then we have an example. Yes. So the procedure is, and this is the proper procedure. Okay. How do you convert the integral part from one base to another? Okay. So how do you do that? For example, if you have a decimal number, again we will assume that we are trying to convert from decimal to another base. Although it does not matter, you can do this conversion from any base to any base in any base. Okay. Now, what does that mean? I'll try to explain it if given the right opportunity and tools. But before that happens, like just absorb whatever I'm trying to communicate here. And again, in the first chapter of your book, so you can find plenty of examples on that. Okay, you can find reasonable number of examples that will help you understand the process. And some of it, like you have learned it in your junior math classes. So I hope like it's not that big a deal. So how do you convert an integer or the integer integral part of a number into any other base? So what you need to do, for example, if you have a number in a certain base and you want to go and convert it into a new radix, so you should divide that number by the new radix. For example, if you have a decimal number, you want to convert it to binary, repeatedly divide that decimal number by the new base, which is 2. So repeatedly divide it by 2. Okay, and save the remainders. The remainders are important. You need to save those remainders. So once you the division, it reaches a point where you cannot divide it any further. Like the quotient is smaller than the new radix, then you should stop. And then you should accumulate all the remainders in reverse order of their computation. The first remainder that you got, you should write it or put it in the rightmost position, and the last remainder should go into the leftmost position. Okay, so first record assuming that you write numbers from left to right, first write the latest remainder that you got, and in the end write the first remainder that you got. Okay, so that is how you'll get that number. Now, why you should do that? Why should it be in such a way? Again, there is a logical explanation for that. We will look at that explanation, and you can verify it as an exercise. You can verify it that it does work like that. Okay, so this is how we are doing it. Now, there is this the explanation is general. This is for any radix to any radix. Okay. Uh, the example that I gave you was for binary only. But for example, if you're trying to convert it into a decimal number into hexadecimal, then the remainder can be anything from 0 to 15. Okay. So if you get remainder that is greater than 9, so you should replace it with the appropriate hexadecimal digits. Okay. A, B, C, D, something like that. How do you convert the fractional part? The fractional part, in order to convert the fractional part, you have to apply the opposite operations that you apply for converting the integral part, and you will accumulate the values of interest in the opposite order uh, as that of the integral part. So how would you convert the fractional part? So if you have a fractional number or the fractional part of a number in a certain base and you want to convert it into a new base, what you need to do is you need to multiply that fractional number 0 point some digits by the new base, and you need to multiply it repeatedly by the new base unless you get like 0. Okay, unless the fractional part of that number, like it is completely finished, there is no fractional part. Okay, or there can be another possibility, unless you start getting a repetitive pattern. Okay, now it may be difficult to explain it in words, but I hope like you will understand it, and there are examples in your book that if you can follow, then it would be much clearer to you. clearer to you. Let's look at an example that we can have here. So say for example we have this number 46.6875. Now it has two parts. This is a decimal number. We want to convert it into base 2, and it has these two parts. What are those two parts? One is the integral part, and the other is the fractional part. So integral part is 46, the fractional part is 0.6875. The procedure is that you should repeatedly divide 46 by the new base, okay, the integral part by the new base. So the new base is 2, so you should repeatedly divide it by 2. So first two 23s are 46. Okay, so it's difficult for me to write it using this on-screen pen, but let's try. And 1 is the, sorry, 0 is the remainder. Okay, you divide 46 by 2, so it's even, the remainder is 0. Now this is the first remainder that you computed. It would appear in the end. Next, divide the new coefficient by 2. Okay, so 2 11s are 22. So what is the remainder that you get? 1. Now divide 11 by 2. Okay, so 2 5s are 10. And what is the remainder that you get? It's 1. Now divide 5 by 2. 2 2s are 4. Okay, and the remainder is 1. And then divide 2 by 2. So 2 1s are 2, and remainder is 0. So 46 in binary would be, start from here, start accumulating or writing from here. This is the latest remainder. This is the first one. So in reverse order, record them in reverse order. 1 0 1 1 1 and then 0. Okay, so this is the integral part in binary. Okay, this is the integral part in binary. Okay, if you do the direct conversion, you can see that it these add up to 46. For example, this is a 2 plus 4 6 plus 8 14. There is no 16 and there is 32. So 32 plus 14 is 46. So this is 46 in base 2. Now how do you convert the fractional part in to base 2? The procedure is, so you want to convert this into base 2, you need to multiply it repeatedly with 2. Okay, so what do we mean by a repeated multiplication? Let us try to demonstrate it here. What do we mean by that? So the first thing that you need to do is you need to multiply this number 0.6875 with 2. Okay, you need to multiply it with 2. So let us do that. So 0.6875 multiplied by 2, it turns out to be 1.375. Okay, it turns out to be 1.375. Now here this 1 is important. Leave it for now. We will use it in the end. We still have a fractional part which is 0.375. Multiply this fractional part with 2 again. Okay, so multiply 0.375 with 2 again. Okay, so if you do that multiplication, you will get 0.75. You will get 0.75. You get 0.75. Okay, now multiply the fractional part with 2 once again, and you have to keep on doing it until the fractional part vanishes. Okay, until the fractional part vanishes. So if you multiply this with 2, you will get 1.5, and then multiply the fractional part with 2 again. So this is the fractional part is 0.5. If you multiply 0.5 with 2, you will get 1.0. Okay, so now the fractional part has become 0. There is no point in multiplying 0 with 2 over and over again, because all you're going to get is 0. So how do we record this fractional part? So you will record it in the order of computation. Okay, so the fractional part would be 0 0.1011. This is the fractional part. Okay, okay, let me clarify the decimal. And what is the number 46.6875 in binary? It is this number. Combine the two. 1 forgive me for my handwriting here. It is not exactly handwriting, but this is the best I can do with this the pen that I'm available. It is not a touch screen, so I cannot use another pen. I wish I had that touchscreen computer, but in any case, this is how you convert a decimal number into binary. Now the procedure is the same for any base system. All you need to do is remember the procedure and pay attention to the details. Okay, but this is how you do it. This is how you convert uh, a decimal number with both integral part and fractional part into a base 2 number. Okay, this is how you do it. And I hope like you know the reverse process. If you are given this number, you should know how to convert it into decimal. So you should know that process, and you have just learned this process as well. So I hope you know that. Okay. Now the fractional part, I said that you stop converting it when the fractional part becomes 0 as a result of repeated multiplication. Okay, but there may be times where it may never happen. Okay, where it may never happen. The fractional part may never become 0. It may start to repeat itself. Okay, say for example, this is another example, 0.65. If you have the decimal number 0.65, try representing 0.65 in binary, and you'll see that this pattern 1001 okay, it somehow starts repeating itself. Okay, so you should verify it. I guess there is some mistake in here, like the way it's written, but you should verify it. Okay, that this is what happens. You get 0.65. In fact, I'll try to assign this as a homework. You get 0.65 and you try to convert it into binary, and you see like what happens. Now what would you do in such a situation? So I guess we mentioned this, that digital systems are by default, like they are finite systems. We do not have unlimited or infinite number of bits to represent numbers or to store numbers. In order to accurately store 0.65 in binary, we would need an infinite number of bits, because this is something that is not ending, that is never ending, and we would need an infinite amount of RAM to store just 0.65. That does not happen. So as you know from your background in computer programming, that we reserve a finite amount of RAM for every type of data. So if you have a character variable, you store it in 8 bits. If you have an integer variable, you store it in 32 bits. If you have a real value, you either store it as float in 32 bits, or you store it as a double in 64 bits. In any case, the number of bits is limited. It's not indefinite or like infinite. So whenever such a situation arises, what you should do is you should specify the number of bits. Okay, I would store it in 1 byte, or in 16 bits, or in 32 bits, or in 64 bits, and this is how it's going to look. Okay, so you truncate it to that number of bits. By truncation, we mean that you remove the extra part of it. Okay, so that is how you'll represent. And you can check your conversion. Again, we did for 46. We verified that 46 has these powers of 2, 32 plus 8 plus 4 plus 2, and they add up to 46. And similarly, the fraction part you can verify. 1 is 0.5, 1 by 8.125, and then 1 by 16. If you add them, you get 0.6875. Okay, so you can always check back your conversion. Why do repeated division and multiplication work again? If you go to the way we represented a number using those summations, and you do this multiplication and repeated multiplication division, you will see or verify that you basically get all those coefficients. Okay. Uh, if you divide a naught by, like if you divide that expression by r, if you keep on dividing it, except for a naught, which is basically a naught by r, or the modulo of a naught by r, the other terms, like, you get them directly. So a1 is basically multiplied by r. If you divide it by r, so you get a1. And the other, you can do this, like, this is very easy. You just take the summation or expression for a certain number of terms, and you repeatedly divide it by r, and you'll see that you are going to get those coefficients. Okay. Similarly, the repeated multiplication, it also works, and you can verify it by doing all those multiplications. Okay. uh, you can do it, like I can also do it in writing. I'll try to demonstrate it, maybe in the next lecture or something like that, but this is easy. You can also verify it. You just need to take this expression. We are talking about this expression. Let me take you to this expression, this one. Okay. So this expression, you expand it, and you expand this one. You repeatedly divide this expression for a certain number of terms, like choose n is equal to 5 and expand it, and then you repeatedly divide it by r, and you see what are the values that you are getting. And similarly, you expand this expression for a certain number of terms, m is equal to 3 or 4, and then you repeatedly multiply it by 2 or by something like that, and then, sorry, by the r or radix that you have chosen. uh, Wait, I have to reply to a text. Okay, so if you repeatedly multiply it by the base in which you are trying to convert it, so you'll see you're going to get these coefficients, these AJs. Okay, and you're going to get these in the same order that I showed you. Okay, so this is what basically this slide is talking about. You go to that summation, that expression, that representation of numbers, their fractional and integer parts, and you do these operations on that, and then you will see that basically you do get all those coefficients. Okay, so this is what this slide is talking about. The next, I guess I mentioned it in our last lecture as well. Octal and hexadecimal, they are basically powers of 2. Octal is base 8, 8 is 2 raised to the power 3, and hexadecimal is base 4, base 16, sorry, and 16 is 2 raised to the power 4. Okay, so 8 and 16, they are powers of 2. If you if you have, for example, 8 different quantities, as you have in the octal number system, you need 3 bits to represent all those quantities. Okay, so if you have 3 bits, the number of possible combinations for those 3 bits, that is 2 raised to power 3 or 8. Okay, I'm worried about the power as well. Power is down here, and I want to know how much charge do I have in my battery. So let me check. Okay, I have enough. Okay, so hexadecimal uh, hexadecimal is basically 16, base 16. And in hexadecimal number system, we have 16 symbols to represent 16 different quantities or numbers. And how many bits would you require to represent 16 different quantities? Okay, so, like, there's a formula. What you can do is you can say log of 16 to the base 2, and whatever is the answer of that, that is the number of bits that you would require to represent 16 different quantities. If you want to know how many bits do I require to represent 8 different quantities, so what you need to do is you should find out log of 8 to the base 2. Like what should be the power of 2 to get 8? So that will give you the number of bits that you need to represent either 8 different quantities or 16 different quantities. So in order to represent 16 different quantities, you need 4 bits, because 2 raised to the power 4 is 16. 2 raised to the power 4 is 16, okay? And 2 raised to the power 3 is 8. So that is the number of bits that you need to require. Now this relationship between binary and octal and binary hexadecimal is very helpful. How is it helpful? For example, if you want to convert an octal number into binary. For example, we have this octal number. This octal number is 7 6. Okay, this is octal number, and we want to convert it into binary. So how would you do it with your current knowledge? With your current knowledge, maybe you'll try to convert it into decimal, and then you'll try to convert decimal into binary. But with this relationship, what you can do is you can replace each octal digit with its 3-bit binary representation. So 7 is basically 1 1 1, and 6 is 1 1 0. Okay, so that is how you can like directly represent it in binary. Just replace every octal digit with its 3-bit binary representation. Similarly, this is octal to binary. If we have a hexadecimal number, say for example, if we have this hexadecimal number, the number is say 6 F and 1. Okay. So this is a hexadecimal number that we want to convert into binary. So how can we do that? Okay, maybe with your current knowledge, you would say, let's first convert it into decimal and then convert that decimal number into binary. But what you can do directly is replace each hexadecimal digit by its 4-bit representation. Okay, so you have to replace each digit by its 4-bit, because that is the number of bits that you require in order to represent any hexadecimal digit. Okay, so what would be the 4 bits that would represent 6? It would be 0 1 1 0. Okay, what is F or 15? So it is basically 8 plus 4 12 plus 2 14 plus 1 15. So this is all ones. This is F or 15. What is 1? No 8, no 4, no 2, just 1. Okay, so this is 1. So we have replaced every single hexadecimal digit with its 4-bit binary representation. That is how you can like move directly from hexadecimal to binary or octal to binary. Why? Because they are powers of 2. Okay, you cannot do the same with decimal to binary. Why? Because 10 is not a power of 2. If 10 were a power of 2 in some universe, then maybe you could like do direct conversion, but it's not the case. So that's why you have to either do the repeated division and all that. Now how do you go in the reverse order? Okay, say for example, if you have a binary number and you want to convert that number into hexadecimal or octal, how would you do that? So let's get a binary number. Let's suppose we have this binary number. Okay, let's add another 0. Let's add a fractional part as well. So it has this fractional part as well. Okay, so let's suppose we want to convert it into octal and then into hexadecimal. How would we do that? Okay, this is a binary number. If you want to convert it into octal, you need to convert the fractional part and integral part separately into octal. How would you do that? So octal is 2 raised to the power 3. So you just make groups of 3 bits, okay, and replace each group of 3 bits with the appropriate with its equivalent octal digit. Now here we have one less bit, so we add or pad it with 0. Similarly here the integer part you start grouping by moving. In either case, you start grouping by moving away from the decimal point. So here you start from the decimal point and you move out towards the left, and here you start from the decimal point and you move out towards the right. Okay, so this is one group of three, this is another group of three. So in octal number system, this would be 2, 6. This is 010 is 2, 110 is 6, 110 is 6, 266 point. Uh, this is 1015, and 101 is 5. Okay, so this is 266.55 in octal. Okay, now how about hexadecimal? If you want to convert this into hexadecimal, so all you need to do is make groups of 4. Okay, so 4 here, and then these 4. That's it. This 0, like we added it as an extra 0 as a padding. And similarly on the fractional part, these 4 and then these 4. So we have 2 here, so we need to add 2 more. So we'll have 4 bits here. Now replace each 4-bit combination with the appropriate hexadecimal digit. Now this is 6. 0110 is 6. And this is 1011. This is basically 11. And 11 is B in hexadecimal. So this is B6. And this is 1011. This is also 11. Okay, B. And 0100, this is 4. So B6 by B4. That would be its representation in hexadecimal number system. That would be its representation in hexadecimal number system. Okay. So that is how you do this conversion from binary to hexadecimal, or binary to octal, or octal to hexadecimal, or hexadecimal, sorry, octal to binary, and hexadecimal to binary. Okay, and it is made easy by the fact that 8 and 16, they are powers of 2, and they have a sort of one-to-one correspondence. Like you need exactly 3 bits to represent an octal digit, and you need exactly 4 bits to represent all hexadecimal digits. All octal digits can be represented using 3 bits, and all hexadecimal digits can be represented using 4 bits. Because of this, we have this convenience. We can move directly from one to another. So I did this example. Okay, uh, you should be able to do this example as well. Okay. Now, this is a final note about conversion. Like when we were converting one number from one base to another base, we usually, like at some point, the decimal was always involved in it. Okay, especially when we were doing it using those repeated divisions. But it is possible to do it in other bases as well. Say, for example, if you have this number, this binary number 10110, and you want to convert this binary number to base 10, but you want to do the conversion in base 10, in binary. Okay, like you don't want the process to take place in decimal, so you can do that. So this is this number, and this is 10 in binary, 1010. This is 10 in binary, so you can do the division in binary. Now the division won't be easy, it would be challenging certainly if you are doing it in binary, because you are not used to doing it, and maybe subconsciously you're doing things in decimal, or consciously you're doing things in decimal, but you can do it. Okay, so this is 4, this is 10 in binary, and this is what is this, this is basically 2 plus 4 6 plus 8 14 plus 32. This is 46. Again, this is 46. So 46 divided by 10 is 4. Okay, but you have to do this division, and this is your remainder 6, and then you can get this 4, try to divide it by 10, so the quotient would be 0, and the remainder 4. So you accumulate these remainders in the reverse order. This is 4, and the other one is 6, so you get 46. So you can do the conversion in any other base system as well. Like in principle, it is possible, but it is not convenient, so that's why we usually do it in decimal. Okay, now in addition to the way we represent binary numbers, we also use something that is called binary coding. Now, numbers and coding, like they are different. Code words are different. Okay. Uh, if you have a number and you want to represent it in binary numbers, so you don't have any liberty. There are certain rules that you need to follow, and you're always going to get a certain representation. That representation will not change. It cannot be changed. Okay, we are talking about numbers right now. So if I give you 46 and I ask you to represent 46 in binary. Okay, so 46 has this representation in binary 101110. You cannot change it. Okay, because there are certain rules. Like in binary, each bit has a certain weight, and if you add those, they add up to 46, and that is how it is. But you can choose to encode 46 in different ways in binary. Like you can represent 46, not the value 46, but you can represent 46 in different using different combinations of the binary ones and zeros, and you will have plenty of liberty that. So whenever we talk about coding, binary coding, so binary coding is different. Like there, you can choose any combinations of ones and zeros to represent anything. Okay, so we will talk about that. So the combinations of ones and zeros that you choose to represent something, that is your code word. Again, this is important. Okay, so we said that computers are used to process different types of data, like all these characters that you see, F and L and E. So these are just characters. These are symbols, and these symbols are stored or represented in a computer using binary ones and zeros. So which combination of ones and zeros should be used to represent an E or an L or a capital F? What should be that? Okay. So for that, you need to design a coding system. How should we code information? Which combination of ones and zeros should represent which particular symbol or which quantity or which color? Okay, anything like that. So that is coding, and we will talk about certain types of coding. When you're trying to represent numeric data, so then usually you go for the direct binary combination. In some cases you may not, like we'll talk about that, but usually it is desirable that you represent them directly in that number system. When you have non-numeric data like text, like colors, like any other thing that you want to process or store on a computer, then you can choose any combination of bits to represent it, because then you will not be adding or subtracting those types of data usually. Like you do not add characters, you do not add them, subtract them, or multiply them. uh, so you just concatenate them, you search for them, and you do these types of operations. So then you can use any combination of bits. But if you have numeric data, since that numeric data needs to be added, subtracted, multiplied, so the representation must be convenient in order to carry out those operations. If that is not the case, then it might not be a very good idea to use that representation. Okay. Okay. So non-numeric binary codes, how are those codes constructed? Non-numeric means if you're trying to represent non-numeric quantities, colors or text or something like that. So how do you create that code? So the first thing is you need to know how many bits do you need. Okay. So first of all, say for example we have these colors 1, 2, 3, 4, 5, 6, 7, 7 colors. So how many bits do we need to represent these 7 colors uniquely? Okay, so we have 7 colors to represent. So if you take the log of 7 to the base 2, you will get some number, and that number will basically tell you the minimum number of bits that you need to uh, represent these colors. Okay, if you have n binary bits, so you can have 2 raised to the power n possible binary combinations, and then that is the total combination. So you can either use all those binary combinations, or you can use a subset of those combinations to represent these quantities. So since we have 7 colors, we need 3 bits at least. 2 bits, we cannot use 2 bits. Why? Because 2 bits will only give us 4 possible combinations. So we'd only be able to represent 4 different colors. 3, we won't have any representation for. We should not be using 4 bits. 2 raised to power 4 is 16. That would be a wastage. More than half of the bit combinations would be unused. So 3 sounds to be a reasonable number. If we use 3 bits to represent each color, so 2 raised to power 3 is 8. So 7 of those 8 combinations would be used. 1 combinations may not be used. Which one? That depends upon you. Uh, well, it depends, and it also depends upon the way you want to code this information. If you look at these uh, these numbers that we have chosen, so each successive number, or these two numbers, like they differ. No, they differ by more than 1 bit. Okay, we'll look at some other codes as well. So this is just an example. If you want to represent non-numeric quantities using binary codes, then the first thing that you need to decide is how many bits do you require to represent those quantities. Okay, so you should know, if you're using n bits, you can have possibly 2 raised to power n unique combinations of ones and zeros. So the maximum number of values that you can represent, or quantities that you can represent, is 2 raised to power n. Okay, so you should know, and then you should choose among those 2 raised to power n bit combinations for those quantities. So we talked about it. Okay, so if you have m quantities and you want to find out how many bits I need, so you need to take the log of m to the base 2. You need to find out what should be the power of 2, so that you can get this something that is either equal to m or less than m. And then we have the ceiling function here. Ceiling function, basically, I hope you have used it in computer programming. There's a ceil function. So you apply the ceil function to a real value, and that ceiling means chat, and opposite to ceiling is a floor function. Okay, so floor is the floor and ceiling is the chat. Now a real number, for example 2.5 or 2.6, it is uh, it is enclosed by two integers. So the smallest integer greater than 2.6 is 3. The smallest integer greater than 2.6 is 3, and the largest integer smaller than 2.6 is 2. Okay, so ceiling gives you the smallest integer greater than a certain real value, and floor gives you the largest integer smaller than a certain value. Okay, so you apply the ceil function, because for example, if you take the log of 10 to the base 2, you're not going to get an integer, you're going to get a fractional number, 3 point something. 2 raised to the power 3 point something would give you 10. Okay, 2 raised to power 3 is 8, 2 raised to power 4 is 16. So 10 would be 2 raised to the power 3 point something. So you need to find out the ceiling value. So if you have 3 point something and you apply the ceil function to it, you are going to get 4. Okay, so the why? Because the smallest integer greater than 3.2 or 3.3, it is 4. So if you are going to represent decimal digits using a binary code, you would need at least 4 bits. You cannot use 8 bits, because they will have you are going to use at least 4 bits. You cannot use 3 bits, because 2 raised to the power 3 is 8, and you have 10 digits to represent. So two of the digits would not be able, you will not be able to represent those. uh, you will be using 4 bits. That will give you 2 raised to power 4 equal to 16 possible combinations. So you would be able to represent 16 different values. If you are using 16, like if you can represent those 16 different values, but in the decimal number system you have only 10 different values, or 10 unique values, so 6 bit combinations would be unused. Okay, so you will have 6 bit combination, 6 extra bit combinations. Now remember this thing, this figure of 6 will appears somewhere else as well when we are using binary coded decimal. Okay, so binary coded decimal is we will be representing decimal digits in the form of codes, 4-bit codes. We will not be representing decimal digits in the form of their binary values, but in the form of their 4-bit binary codes. Okay, so that is called binary coded decimal. And then we would also like to do carry out operations on those binary coded decimal digits. So that will basically involve this number 6 again, like we'll return to it. It will have some bearing there. Okay, so we know, like, if we have n digits in radix r, there are r raised to the power n distinct elements that can be represented. So if r is 10, for example, if you have two decimal digits, so you can have 10 raised to power 2, which is 100 unique combinations: 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0, 8, 0, 9, 1, 0, 1, 1, up until 99. Okay. If you have two hexadecimal digits, so you are going to have 16 raised to power 2, that is 256 possible combinations. If you have two octal digits, you are going to have 8 raised to power 2 or 64 possible combinations. So for any base system, this is what you're going to have. Here we have, you can represent 4 elements in radix r is equal to 2 with, if you have 2 digits and the base is 2, so you can have 4 possible combinations. Okay. If we have 4 digits in base 2, like if we have 4 bits, so we can, the possible elements that we can have is 2 raised to power 4, 16. We can have 16 possible combinations. Okay. But if we have 4 elements to represent, so we can choose any of those 16 possible combinations to represent those 4 elements. So this is an example of a code which is called one hot code. One hot means one of the 4 bits here is 1, the rest are 0. Okay, and since we have 4 bits, so if we are using one hot code, so we can only have 4 possible elements. One hot code is a code in which only one of the bits is high, all the other bits are 0. Okay, that is a one hot code. So although we have 4 bits and total 16 possible combinations, but out of those 16 possible combinations, there are only 4 in which only one bit is high and the other are 0. This is one hot code. It is important in some applications in FPGAs, field programmable gate arrays. Uh, Once upon a time when we used to work with those, so we typically use the one hot code to represent different things. Okay, so it makes certain aspects of the design simpler. Okay. Now binary codes for decimal digits. How are decimal digits, like how can decimal digits be represented in binary? Now there are a few codes that are commonly used. One is the simple code, that is the direct binary representation. This is the direct binary representation or direct binary value of this decimal digit. It is also called the 8421 code. Now these are basically the weights. Okay, so 1 is the weight of this bit position, 2 is the weight of this bit position, 4 is the weight of this bit position, 8 is the weight of this bit position. So the first one is the 8421 code. Okay, so we can represent decimal digits in the form of this code. Now, when we are representing a decimal digit using this code, so what we are going to do is we are going to replace each decimal digit using one of using their 4-bit representation. For example, if we have this number, say 46, and we want to represent 46 in 8421 code, so we are not going to convert 46 into binary. Instead, we are going to replace each decimal digit with its code. So in the 8421 code, we are going to replace 4 by its code, which is 0100, 0100, and 6 is basically 0 1 double 0 double 1 0 0 double So this is 46 in the binary coded decimal. Okay, 46 in the 8421 code. Okay, it is not a direct conversion of 46. Like we did not repeatedly divide 46. If you find the decimal value of this code, it may not add up to 46, or it may. Let's see. So this is 2 plus 4, 6, and this is there is no 8, no 16, no 32, and then there is 128. Okay, so its value is 134. It's a binary value. But since we are using a binary code to represent these decimal numbers, so we do not do the conversion. We just replace each decimal digit by its 4-bit code, just like you would use ASCII code to represent these characters. If I ask you how would you represent there, THERE, with in ASCII, so what you would do is you would replace each alphabet with its 8-bit ASCII code. So T's ASCII code, then H's ASCII code, and E, R, E. So this is exactly the same here. So we have these digits, decimal digits, but we do not want to convert it directly into binary using those techniques that we just studied. We want to represent each decimal digit as a unique using a unique binary code. Okay, and these are the different coding systems that we have. So we can have 8421 code in which 46 would be represented this way. Then we have XS3 code. So XS3, like it means XS3, 3 extra. So 0 is basically 0 plus 3. So this is binary 3. This is the code for 3. This is XS3 code. So how would you represent 0 in XS3 code? It would be 0 plus 3 or 0011. 1 is 1 plus 3 or 4. 2 plus 3 or 5. 3 is 3 plus 3 or 6, and 7, and so on. So how would you represent 46 in XS3? So what is the XS3 code of 4? It is 0111. It is 0111. And what is the XS3 code of 6? It is 1001. That is the XS3 code of 6. 9 basically. So this is 46 in XS3 code. Then we have 8, 4, minus 2, minus 1 code. Okay. So what is 8, 4, minus? These are basically weights of these bit position. 8 is the weight of this position, this position, this position, this position. Now this is a code. You can design any code using any technique. Okay. This is totally up to you. Now the person who designed this code, like that person did it by assigning these two different weights to the last two bits, the least significant two bits. Okay, so for example, look at this value. You can calculate its value. It is basically 1. So how do you get 1? 4 minus 2 minus 1. So its weight is 4, and its weight is minus 2 minus 1. So this is 4 minus 2, 2 minus 1, 1. This is 4 minus 2, which is equal to 2. This is 4 minus 1, 3. This is 4 minus 0. 5 is basically 8 minus 2 minus 1, 8 minus 3. Okay. 6 is 8, uh, 8 minus 2. Okay, 8 minus 2. 7 is 8 minus 1. 9 is, sorry, 8 is 8 minus 0. And 9 is 8 plus 4, 12, minus 2, 10, minus 1, 9. Okay, so this is the 8, 4, minus 2, minus 1 code. Now, if you want to represent 46 using this code, how would you represent it? You just pick up the codes. This is 4 is 0, 1, 0. 4 is 0, 1, 0, 0. And 6 is 1, 0, 1, 0. 6 is 1, 0, 1, 0. That is how 46 is going to look in the 8, 4, minus 2, minus 1 code. Then we have the gray code. The gray code is also a special code. Why is it special? Because if you look at these adjacent code values, they only differ by a single bit. So if you look at these two codes, they only differ by this bit. Rest are all the same. If you look at these two codes, they only differ by this bit. Okay, they differ by this bit. They differ by this bit. If you look at these, they differ by this bit. These two differ by this bit. These two differ by this bit. These two differ by this bit. Now the gray code is also important in certain applications, like maybe in future in some courses in MSD or instrumentation, you'll study about optical shaft encoder. So you want if you want to know the position of the shaft, you can use an optical encoder to tell you about the position of the shaft. And those optical encoders, they typically use these gray codes in order to give you the unique position of those things. Okay, so gray code and this is you can also use gray code to represent 46. How would you do that? 4 is 0110, 4 is 0110 in gray code, and 6 is 001, 6 is 001. So this is how 46 would look in gray code. Okay, this is how it would look in gray code. Okay, so binary coded decimal among these is the 8421 code. This is the simplest code among these. Like, it is just direct conversion, direct binary value of these decimal digits. So this is this system is like simplest among these four coding systems that we uh, talked about, that can be used to encode decimal digits. Uh, okay. This code is the simplest and most intuitive binary code for decimal and uses the same powers of 2 as binary numbers, but like we are only encoding digits from 0 to 9 because that is the number of decimal digits that we have. So again, this is simple. It's not that difficult. In the BCD, we are talking about here invalid code words. So BCD is a 4-bit code. We have 16 total combinations or code words. Out of those 16 we use these 10 codes. We use these 10 codes to represent the decimal digits, and the remaining codes we don't use. They are invalid codes in the BCD code. Okay, and what are those codes? So those codes are basically 1010, 1011, and then 1100, 1101, 1110, and then all ones. So those code words are invalid code words. Okay, so if a system is using the BCD, binary coded decimal system, and one of those code words appear, so that system will not be able to recognize that code, okay, because it does not map to any decimal digit. Okay, then if you look at these two codes, there are some interesting properties of this code. What are the interesting properties? The interesting property is that these are called complement codes. So if you have the code for 0, you can get the code for 9 or 9 minus 0 by just flipping the bits. So make the ones as zeros and the zeros as ones. Similarly, if you have the code for 1, you can get the code for its complement. If you add the 2, you should get 9. So by flipping the bits. So this is 0110, 0100. So the code for 8 would be 1011. Okay, 1011. Or if you have this code, just flip the bits and you will get the code for this one. Similarly, the 84 minus 2, this is also a complement code. So if you have the code for 0, the code for 9 you can get by simply flipping the bits. If you have the code for 8, you can get the code for 1 by simply flipping the bits. Okay. Uh, Flipping the bits means converting ones into zeros and zeros into ones. So this is the code for 7. So the code for 2 you can get by flipping the bits. So 0, 1, 1, 0. That would be the code for 2. This is a property of XS3 and this 8, 4, minus 2, minus 1 code. And we talked about the property of gray code. the adjacent uh, bit positions, they differ only by a single bit. Okay, the gray code in the gray code, the adjacent decimal digits. So these are adjacent. Okay, these two are adjacent. These two are adjacent. These two are adjacent. ठीक है? Consecutive. The code for consecutive decimal digits, either upwards or downwards when you're counting upwards or downwards. So those codes they differ by only a single bit. Now this is important. Okay, it is important if we are using something like optical shaft encoder. Okay, again a warning here. Do not mix up conversion or coding. Conversion is different. If I ask you to convert a decimal number into binary or a binary number into decimal, this is different. It is the procedure for it is the same, like repeated division by 2 and all that. If I ask you or if somebody asks you to code a decimal number with a binary code, that is different. And this is an example. So 13, if you want to convert it into binary, so this is what you get. Okay, you do repeated division and this is what you get. So this is the power, this is 2 raised to power 0, 1 plus 4, 5 plus 8, 13. If somebody asks you to code it, so this is how you code it. You replace 1 by its 4-bit code, BCD code. You replace 3 by its 4-bit BCD code. This is how you code it. This is coding and this is conversion, and you should be clear about this. Okay, the next thing is binary arithmetic. I guess we should leave it for the next lecture. In the next lecture, we'll start from here. We'll talk about how arithmetic is done in binary. We'll do the addition, subtraction, multiplication, both. We'll start with single bits and then we will move on to multiple bits. Okay, so that we'll do in the next lecture. I hope you this lecture was useful for you. If you have any questions, like I want you to go through this video and try to absorb the material. If you have any questions, you can write down those questions, and inshallah we'll address those questions on Monday when we'll meet again for another session of TLD. Okay. Until then, fi amanillah.